So hello and welcome to Algebra 1. So I am one of the TAs for this course. My name is Shubhajit Dash and welcome to week 12. Okay. So this particular week you have been studying about various interesting theorems like the structure theorem for finitely generated modules over a PID, and then you have also studied the rational canonical form and the Jordan canonical form of a matrix. So the problems will be based on those. So I hope you are attending Harish's sessions as well, and so uh, every week we solve problems from the previous year assignment. So this is our final week. So let's start. So as you have already understood that the rational canonical form and the Jordan canonical form, they are interesting. They are rather sort of brilliant ways to capture nice interesting properties of a matrix. So if you have a huge matrix, the matrix might be very complicated to deal with, but working with the rational canonical form and the Jordan canonical form sort of reduces the complexity. Now there was a problem with the rational canonical form as well, because we saw that it sort of obscures all the various interesting and important properties of a matrix, such as diagonalizability for instance, which is why we wanted to obtain a much more stronger form, and that is why you you studied Jordan canonical form as well. So anyway, so let us start solving the problems one by one. So let's read out the solution question first. So question 1 says that we need to determine whether this statement is true or false, that as a Z module, in other words as an abelian group, the ideal generated by some D is P primary if this holds, that if you take the coset of the ideal generated by D which contains 1, that particular coset containing 1, and if you just multiply by P to the power K, that is P to the power K as a scalar, then this is equal to the ideal generated by D, which is equivalent to saying that P to the power K is in the ideal generated by D, or in other words D divides P to the power K for some K greater than 0. So if this particular thing holds, that D divides P to the power K, then is it true that the ideal generated by D is P primary? So the obvious answer is certainly false, right? Because firstly Z is completely torsion free, right? So it doesn't there is nothing, so P primariness is completely trivial for Z, right? We can just so this is false. Let us just take an example. So take let's take D. So our module is Z. Let's take D to be 1. Okay, then the ideal generated by D is equal to all of Z, right? And clearly P to the power 1 plus ideal generated by P to the power K is equal to ideal generated by D, right? As the simple reason being that P to the power K is in Z, right? But Z, which is ideal generated by D, is clearly not P primary, right? So P primariness, if you recall, basically means that, so you take some module M, and suppose you are taking that module over a PID, for example, and suppose P is a prime in the ring of scalars, okay, then the P primary part of M was basically the set of all elements of M which are annihilated by some positive power of P, right? And the module itself is called P primary if it is equal to some P primary part of itself. That is, if every element of the module is annihilated by some positive power, and clearly Z is not P primary, right, for any prime P. So this is certainly false. There is nothing more to this problem. It's very easy. Anyways, so let's move on to the next question. So which of the following holds if and only if two matrices A and B are similar. Okay, so this is sort of trying to find an equivalent condition for similarity. So we need to determine which of the following holds if and only if the two matrices A and B are similar, right? So let us read out the statements one by one. Firstly, A and B are equivalent. Secondly, A and B have the same null space. Thirdly, Ti minus A and Ti minus B are equivalent. And fourthly, Ti minus A and Ti minus B have the same Smith normal form. So Ravi, would you like to try this one? Okay. Yeah, but I don't think you have done this problem, right? Yeah. So do you want to try this one? So this is about finding some equivalent condition for similarity of two matrices. Okay. So A and B are similar if and only if which of these following would hold. So this is, so the question, you know similarity of matrices, right? Right? So basically you are asked to find out an equivalent condition for similarity of the matrices A and B. So suppose, so basically A and B are similar if and only if which of these following will hold. That is, which of these following four statements are equivalent to the similarity of A and B. Okay. So we claim that C is true, C is correct, and the reason is very easy actually. You have in this week's main sessions, you have seen this, that A is similar to B. I might not be correct with the notation, so I'll just write it in words. A is similar to B if and only if. So when do we say that? So what this theorem says is that A is similar to B if and only if the module MA is isomorphic to the module MB, right? As KT module. Suppose the matrices are taken over a field K, okay, as KT modules, right? This you have seen, right, this week in the session. The modules should be equivalent, I mean isomorphic. So MA is isomorphic to MB as KT modules, which is equivalent to saying, now you already know what MA looks like, right? It is a free module KT power n modulo the column space of Ti minus A, right? This also you have seen maybe in the previous week lecture on Smith normal forms and all that, but this week they have again mentioned this. So isomorphic to KT power n modulo the column space of Ti minus B, right? So basically one is, so this is MA and this is MB, right? Right? KT power n modulo column space of Ti minus A is isomorphic to KT power n modulo the column space of Ti minus B, which is which is equivalent to saying, now you know that whenever you have two modules of this form where it's a free modulo some column space of some matrix, and on the other hand, on the other side you have the same thing, then these two modules will be isomorphic provided the matrices are actually equivalent, right? This also you have seen in the lecture on the Smith normal form. So that is, so this is true if and only if Ti minus A is equivalent to Ti minus B, right? Okay. Correct. So both C and D actually have to be correct. Anyways, so this much you know, right? Because you have seen this in the sessions, right? This was used to when the instructor was trying to sort of develop the rational canonical form. He was using this, right? So Ti minus A is equivalent to Ti minus B, and you definitely know this, that two matrices are equivalent if and only if they are the same Smith normal form, right? So which is true if and only if Ti minus A and Ti minus B have the same Smith normal form. Okay. I hope you don't have a problem with this, right? Yeah. So certainly C and D are correct, but what about options A and B? So we see that this is A and B are definitely not correct, and the reason is very easy. Okay, let me just make some space. Yes, 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 and conversely as well, right? If they are equivalent, they will have the same Smith normal form, right? Isn't it? Yes. Just a moment, okay? Just yeah. So certainly C and D are correct, but what about options A and B? So we claim that both of them are false. So similarity is not actually equivalent to the equivalence of matrices, and at the same time, two matrices A and B are similar. This fact or statement is not equivalent to saying that A and B have the same null space. Okay. So clearly you understand that certain similarity certainly implies. Just a moment, okay. I don't know why is it making such an odd sound. 1 minute. Is it okay? Okay. So yeah. So yeah. So certainly you understand that similarity of two matrices implies that the two matrices are equivalent, right? Because if A and B are similar, then B is some P inverse A P, right? And therefore A and B are equivalent as well. Because for the definition of equivalence, you just need that B should be equal to some Q A P, where Q and P are invertible matrices, right? So if you already have that B is equal to P inverse AP, so if you already have that Q is equal to P inverse AP, I mean B is equal to P inverse AP, yeah. So yeah, if you already have this, then they are certainly equivalent, right? So similarity implies equivalence, right? But we want, what we want to show is that the converse. Yeah. Yes, always, always. Because two matrices A and B are similar means that B is equal to P inverse AP. You agree, right? Now, what is the definition of equivalence of two matrices A and B? A and B are equivalent if there exist matrices Q and P which are invertible such that B is Q times A times P, right? So you can just take, suppose A and B are similar, you can just take Q to be P inverse, right? So then B is equal to P inverse AP, which means that they are equivalent as well, right? Yeah. So similarity certainly implies equivalence, but for what we want to show is that the converse is not true, right? That equivalence is not, doesn't imply similarity, and the reason is very easy. So you take, so A is not correct. Why? Because take the matrix A to be identity matrix. Okay. Let B be let B be some invertible matrix. invertible matrix. Okay, and by the way, I am assuming that A and B are square matrices of the same order. Okay, so anyways, so let B be some invertible matrix. Then I can clearly write I can write B is equal to B I, let's say B I, what should I say, B I, okay, which implies that B is equivalent to I, right? Because the definition of equivalence, you can come up with matrices Q and P which are invertible such that B is equal to Q A P, right? So that means in this case B and I are equivalent, but can B be similar to I? But B is not similar to I. Why? As otherwise, yeah, I should also mention something here. I am taking B to be some invertible matrix which is not I, which is not identity. Yeah. So anyway, so can B be similar to I? No, right? As otherwise, B would be equal to some P inverse IP, which is equal to I, right? Isn't it? So the point is that the only matrix which is similar to the identity matrix is the identity matrix itself. No other matrix can be similar to identity. But as we clearly saw, any invertible matrix is always equivalent to identity. So equivalence doesn't imply similarity, right? And for the same reason, option B is also not correct, as B as A equal to I and B belonging to, yes, any, yes, yes. So B is not correct as A, as I'm just taking the same thing. I'm taking A to be identity matrix and B to be GLNK minus I. Just a moment, Ravi. I'll just switch this off. Chua. Yeah, sorry for this disturbance. So I'm taking for the second option, I'm saying that it's not correct, as I'm taking the same example again. I'm taking A to be identity matrix and I'm taking B to be some invertible matrix which is not identity. Okay, then A and B have the same column space, right? I mean, sorry, null space, right? Just taking A is equal to this and B is equal to this implies that A and B have the same null space, right? What is a null space? What is the null space of the identity matrix? What is the null space of the identity matrix, Ravi? What is the kernel of the identity matrix? That is what null space means, right? Can you hear me? Hello? Hello, you can hear me, right? Hello? Hello? So A and B have the same null space. What is the null space of the identity matrix? It's just 0, right? Because it's injective, and injective means it has trivial kernel. And similarly, B has been taken to be some invertible matrix, which means that it is again injective, so it has trivial kernel. So they have the same null space, but A is not Yeah, what I'm saying is I'm taking A to be the identity to be the identity matrix and B to be some invertible matrix which is different from identity. Okay. Okay. Just as I took for proving that A is not correct, I took the same thing. A is identity and B is some invertible matrix which is not identity. I am doing the same thing for option B as well. I am taking A to be the identity matrix and B to be some invertible matrix which is not identity. Okay. So then A and B have the same null space 0, right? A and B both are invertible, hence injective, hence they have trivial kernel or trivial null space. But A is not similar to B, as we clearly saw, because the only matrix which is similar to identity matrix is the identity matrix itself. So certainly option B is also not correct, that if A and B have the same null space, that this is equivalent to saying that this A and B are similar. This is wrong. This is not correct, right? So certainly option A and option B are incorrect and option C and option D are correct. Okay. So let us move on to, do you have any questions? So let's move on to the next question. Yeah. So question 3 is about finding the companion matrix for this particular polynomial. So as you know, the companion matrix, more precisely known as a Frobenius companion matrix, what does it do? So it associates to every polynomial some matrix, right? Now it's not an arbitrary association. You know the way in which the companion matrix is formed for a given polynomial. But even something more important is this, that given any matrix, if you consider its companion matrix, and the companion matrix has the same characteristic polynomial as this given, given any polynomial, if you consider its companion matrix, then the companion matrix has the same characteristic polynomial as a given polynomial, and it has the same minimal polynomial as a given polynomial, right? This is what makes the companion matrix so powerful. So anyways, our polynomial is pt is equal to t cube plus 2t square minus t plus 1. So what is the companion matrix? So just recall, even though we don't need this here, but just recall that suppose I am taking this in some kt, then kt mod the ideal generated by pt is actually isomorphic to m c pt. What is cpt? cpt is the companion matrix of pt. So from this description, by considering the canonical basis of kt mod ideal generated by pt and looking at the action of t, you can determine what is cpt, but we already know what it looks like, so let us just quickly write it down. So the companion matrix of pt is this, right? So first of all, what should be the dimension of this matrix? As we can clearly see, this particular polynomial has degree 3, which means that the dimension of this matrix should be 3 cross 3, right? So you take 0 1 0, then you take 0 0 1, and finally what you do is you just write the coefficients of the given polynomial in reverse order, right? So the constant term, which is 1, you just write its negative here, then the term coming after that, which is the coefficient of t is -1, so minus of -1 is 1, and then the coefficient of t square is 2, so you take its negative again, so -2, right? So this is the companion matrix of pt, right Ravi? I hope you have seen companion matrices during this week. It was considered, it was taught this week, right? Right? Hello, you can hear me, right? Hello, you can hear me, right? There's no problem with my Wi-Fi. Maybe you are having some internet problem. Anyways, I hope. Uh, okay, so maybe yeah. So hello, hello. You can hear me, right? Okay. So if you have any questions and you are not able to sort of ask me directly because of your maybe you are having some internet problems, so you can just write down in the chat. So this is the companion matrix, and okay, so this is the companion matrix, and you have seen this particularly. So yeah, so for this particular polynomial the companion matrix looks like this. So let us move on to the next problem, which is a question about the rational canonical form. So suppose that ma is kt. So a is some matrix, and suppose that the yes. So here a modulo. Yeah, this was also mentioned in the class, right? I saw that video. But anyways, so basically, so suppose so the so basically suppose CPT is a companion matrix of PT. Then if you consider the module MCPT, this will be isomorphic to the quotient KT modulo ideal generated by PT. This is what I am saying. Okay, these two are isomorphic as KT modules, isn't it? Yeah. So basically, what I'm trying to say is that MCPT, if you consider MCPT, then this is actually a cyclic module. Okay. And this is isomorphic to KT modulo ideal generated by PT. This is what I'm trying to say. It looks like, as any quotient ring looks like, the elements are the cosets of the ideal generated by PT, right? And what we saw is that it is actually isomorphic to MCPT. You understand what MCPT looks like, right? Yes, yes. So basically, MCPT, what was it actually? You consider, suppose CPT has degree n in general. So you consider Kn, and what is a the linear transformation in this case from Kn to Kn is just multiplication by the companion matrix CPT. Now this linear transformation induces a KT module structure on CPT, right? I mean Kn. It induces a KT module structure on Kn, and this KT module is what MCPT is. And what we are saying here is that this quotient module KT modulo ideal gen by PT is actually isomorphic to MCPT. So you have a description, sort of a dictionary, how KT modulo this ideal looks like, or maybe how MCPT actually looks like, and so on. Okay. So let us move on to the next problem. So let MA is equal to KT modulo ideal gen by PT direct sum KT modulo ideal gen by QT. So MA is this particular module. MA is this particular KT module, where you are given that the rational canonical form for A is given like this. Okay. You need to determine what are PT and QT. So if you just recall, how was the rational canonical form sort of derived, right? So you took a matrix A, then you considered the module MA, you applied the structure theorem for finitely generated modules over the PID KT, right? And you decompose it as a direct sum of, as I have written here, you decompose it as a direct sum KT modulo sum ideal, direct sum KT modulo sum ideal, and so on. And what did you do after that? So this is just repeating what the instructor said this week, that so suppose M is a module which comes from a matrix MA, N is a module which comes from a matrix uh, B, let's say, then M direct sum N actually is isomorphic to this block matrix, right? A00B, right? So using this description we can find out what KT modulo ideal generated by PT is, right? I mean direct sum okay, so let me write it nicely. So let me write this nicely. So recall This is essentially deriving the rational canonical form again. So recall this, and kt modulo ideal joined by pt. What is this? As we know, this is m of the companion matrix, right? cpt. And what is this? m. What is a companion matrix of pt? So yeah, we don't know this as such as yet. And what is kt modulo ideal joined by qt? This is m of the companion matrix of qt, right? And now using what we have written here, so we know that ma is isomorphic to kt. This is given to us, modulo ideal joined by pt, right? Direct sum kt modulo ideal joined by qt, and this is isomorphic to mcpt direct sum mcqt. But we know now that this is isomorphic to mcpt. I mean this block matrix 0. Yeah, let me write it nicely. mcpt 0 0 cqt, this particular block matrix, right? Which implies that A is similar to cpt 0 0 cqt. So this matrix cpt 0 0 cqt, this is a block matrix, and this is what the rational canonical form of the matrix A is. Now we are given the rational canonical form to be this, right? So we just sort of give the partition of the blocks, and then we are done. So this is one block, right? So this is the first one is a 3x3 block, and the second one is a 2x2 block, and the rest is all zeros, right? This is our partition. So the top one is the companion matrix of, let's say, the polynomial pt, and the bottom one is the companion matrix of the polynomial qt. Thus pt has, yeah, so as I was saying that, yeah, so thus pt has companion matrix 0 0 0 1 0 minus 1 1 0 minus 1 and 0 0 1, right? This is the companion matrix of pt, and qt has companion matrix 0 minus 1 1 1. Okay, so pt has companion matrix this, and qt has companion matrix this, and hence we therefore can find out the polynomial pt. Thus p of t is equal to, so what is this? So p of t will be, so you just look at this column, right? This is where the coefficients of the polynomial p lies. So pt will be equal to, it's a 3x3 matrix, that means it will be p cube, and then you have 1 at the bottom, right, which is the coefficient of t square. Rather, its negative will be the coefficient of t square. So t cube minus t square, and then you have plus t, because you have minus 1, right, in the third column and second row. So that means you'll take its negative, so plus t, and then the leading coefficient is 0, right? And qt is equal to, it's a 2x2 matrix, so t square, and just look at this particular column, minus 1 1. So the coefficient at the bottom is the coefficient of t, right? So it's minus t, and then you have minus 1, so you have plus 1, right? Minus 1 means you will take its negative, right? This is how companion matrix is formed. So pt is this and qt is this. Is it okay? Did you understand? You know this is, right? Yeah, good. So let's move on to the next problem. just make sure. Yeah. So question 5, again an easy problem. So let ei be t minus lambda power I. Okay. So that E0, E1, E2 and E3, this set is a basis for the module m is equal to Ct modulo t minus lambda power 4. You already know what Ct modulo t minus lambda power 4 is, and you are taking a, you are taking, so ei as a polynomial is in Ct, and you are taking its image in the quotient. You are taking its corresponding coset in this quotient m. So m is this particular Ct module, and you are taking this basis. So which of the following is an eigenvector for the action of t on m? Okay. So we already know that we have an action, right, of t on m. T acts on m, which is just multiplication by t. We just need to determine which one of them is an eigenvector for the action of t on m. Now t is a linear map, and t of ei is just t times t minus lambda power I. Yeah, I should write it as a coset because it is an element of this quotient, right? M, Ct modulo t minus lambda power 4. So t times this t minus lambda power I plus t minus lambda power 4, right? So this is your ideal. Yeah, I should also write the ideal. I don't know why they never write the ideal symbol, but it should be written. Ideal generated by this. Yeah, now it's okay. So t times this, right? So you can write this as t. So this is just t times t minus lambda power I plus t minus lambda power 4. Yeah, and then this is t minus lambda power I plus 1 minus plus lambda times t minus lambda power I, right? This is what you have seen this week, isn't it? While the instructor was trying to develop the Jordan canonical form, he mentioned this. So this is a representative, and you need to write the ideal as well because you are working with cosets, right? So the point is, this is what it is, right? T minus lambda power I plus 1 plus lambda times t minus lambda power I. Okay, it's all right? And then this is, what is t minus lambda power I plus 1? This is ei plus 1 plus lambda times ei plus t minus lambda power 4, the ideal generated by this, right? This is the coset of the ideal generated by t minus lambda power 4. Now the question is, when is this an eigenvalue? When is, eigenvector, when is ei an eigenvector? T is a linear map from M to M, right? Multiplication by T is a linear map from M to M, precisely how KT modules were defined. And now what you do is, EI, now the point is that EI is an eigenvector of this linear map, provided there is some constant, let's say C, says that TEI is equal to CEI, right? Isn't it? So we just need to find out when is EI a scalar multiple of TEI. Scalars should come from the base field, right? As is the case for eigenvectors and eigenvalues. So certainly if I is equal to 0, 1, 2, then ei plus 1 is certainly non-zero, right? As what is ei plus 1? It's just t minus lambda power, ti plus 1 plus, I should write it properly, ei plus 1 plus t minus lambda power 4, the ideal generated by this is non-zero. That is, it's not, that is ei plus 1 is not in the ideal generated by t minus lambda power 4. Why? As t minus lambda power I plus 1 is equal to ei plus 1 is not in t minus lambda power 4, the ideal generated by this, for I is equal to 0, 1, 2, right? If I is 0, then t minus lambda power I plus 1 is just t minus lambda. If I is 1, it's t minus lambda power 2. If I is 2, it's t minus lambda power 3. But none of them can belong to the ideal generated by t minus lambda power 4, right? As otherwise t minus lambda power 4 would divide a power of it smaller than 4, which is impossible, right? Right? Thus, now, yes, and one more thing is, and E3, I mean t times E3 is t minus lambda power 4 plus t minus lambda plus lambda times t minus lambda power 3 plus ideal gen by t minus lambda power 4, right? But then t minus lambda power 4 is in the coset, is in the ideal t minus lambda power 4. So that means this vanishes. So you are just left with lambda times t minus lambda power 3 plus t minus lambda power 4, the ideal gen by this. So this is just lambda times E3, right? So I am using some abuse of notation. At times I am writing the full coset and at times I am writing the representative, but it's clear, right? So which implies that E3 is an eigenvector, right? Because it's a t times E3 is a scalar multiple of E3. Okay, for the action of t. Is it clear to you? It's very easy, right? We are just using the definition of an eigenvector. Okay. Yeah. If you have any question, you can always ask me. If something is not clear, then just ask me. We are just using the definition of an eigenvector. We are just observing which of these four vectors, whenever t is applied to which, t applied to which of these four vectors gives you the vector, gives you a scalar multiple of the same vector. And we saw that only E3 satisfies this. E0, E1 and E2 don't, right? Because for I is equal to 0, 1 or 2, Ei plus 1 is not in the ideal generated by t minus lambda power 4, right? And that is why this is the case. Okay, so let us move on to the next problem. Please just feel free to. Yes. Yes. For E1 and E2, the what is E1? It's t minus lambda, right? It's t minus lambda power 1. That is t minus lambda, right? But can it lie in the ideal generated by t minus lambda power 4? No, right? Because in that ideal, then t minus lambda power 4 would divide t minus lambda. Yes. So only possibility is that I is 3, in which case E3 clearly lies in E4 clearly lies in t minus lambda power 4, right? So what is TEI? TEI is EI plus 1 plus lambda times EI plus t minus lambda power 4. It's this, right? This particular line that I have written. So if you take I to be equal to 3, then EI plus 1 is just E4, that is t minus lambda power 4. So that vanishes. That belongs to the coset, means that belongs to the ideal, means that it vanishes as a coset, which means that you are only left with TEI is equal to lambda EI, or rather the coset of lambda EI, right? Which means that EI is an eigenvector, right? Okay. It's all right, right? Let me just write this precisely so that people don't get confused. So TEI, by TEI what I am actually trying to say is TEI plus t minus lambda power 4. Yeah, now it's correct. Yeah, okay. So let's move on to the next problem. This is very easy. This is rather, we are taking a few steps backward and asking something here. This is even before you studied the rational canonical form and the Jordan canonical form. Okay. So let A belong to M and F, and which of the following are true for the FT module MA. Okay. So firstly, MA is finitely generated as an FT module, and secondly, torsion part of MA is equal to MA. So I would first ask you this one. What do you think? Which of them are correct? Is the first one correct, that MA is finitely generated as an FT module? Of course, it seems true and it should be true, right? Because this is precisely what the entire theory of rational canonical form and Jordan canonical form is based. MA, what is MA? A is an A is an n cross n matrix. So what is MA? As a set, it is precisely k power n, right? Or rather f power n, right? So, so what I want to say is that both A and B are actually correct. Correct. So MA is the FT module induced by the action of A on F power n, right? This is what I'm not breaking this statement again. We have been seeing this for several weeks now. What is this so-called FT module MA, right? So basically, A is a linear map from Fn to Fn, since it's an n by n matrix. So A is a linear map from Fn to Fn, and using this you can define a module's FT module structure on this Fn, right? So you take t, what is t dot some vector in Fn, it's just A, the matrix A applied on that vector, right? And then you sort of extend it to all the polynomials. This is what your MA is. So MA is the FT module induced by the action of A on Fn, right? And since this action of FT on Fn extends the original vector space action, extends the field action or action of F on Fn, as we saw. That is, you have those constant polynomials which behave as your elements of F, right? So since this extends the action of F on Fn, hence what I want to say is, hence Fn is Fn, that is MA. Fn is the same as MA, is finitely generated as an FT module, right? But precisely because Fn as a vector space over F is finitely generated by n many vectors, right? So that means that the same vectors will generate Fn as a module over Ft, right? Because you already have F sitting inside Ft, those scalars give you the entire Fn, right? That means if you just you now have more polynomials to work with. So if you just keep on making the polynomials act, in particular the constant polynomials will act, right? That means Fn is automatically generated as an Ft module, right? Isn't it? Oh, okay. Yeah, sure. So basically you take Fn, you consider is it as a vector space over F. It is finitely generated, right? There's no doubt about that, right? Fn as a vector space over F is finitely generated, right? You just take the canonical basis E1, E2 up to En, right? Ravi? Maybe you can reply in the chat if you are facing internet problems. Hello? Hello? Oh, yeah. So Fn is finitely generated as an F vector space. Now what is the Ft action? Whatever way Ft acts on Fn, this action extends the action of F, right? That we also know. Correct? So if suppose E1 up to En generate Fn as a vector space over F, right? Then E1 up to En will also generate Fn as a module over Ft, right? Sorry, did you understand? Yeah. I mean it, not f of t, they will generate fn as an ft module. So what is ft? Ft in particular contains f, right? So it is, so we see that it is just sufficient to take scalars from f and they will generate, I mean they will help us I mean this scalars supplied as coefficients to the e1 up to en generate fn. So if you, so what is ft? Ft contains these scalars and some more objects, right, more polynomials, right? So in particular it contains those scalars, right? So it will definitely generate fn, right? Since f generates fn, ft will also generate, I mean the scalars from ft will generate fn, right? I mean the generating elements are e1 up to en, but and the coefficients are supplied from f, and this will give you the this will give you the this will give you fn in its entirety, right? Yeah. So the reason is that f contains ft. I mean ft contains f. So fn is finitely generated as an ft module. Okay. And why is option B correct? This is interesting. Why is B correct? Why is the torsion part of ma equal to ma? In other words, what this says is that ma is a torsion module, that is it has no free part. So why is this correct? You know what torsion is, right? Yes. No, I will explain it, but it's surprising because you are attending the sessions every week, right? Torsion. Oh, I see. I see. Oh, I see. Yeah, but yeah. Anyways, torsions. No, it's okay. What I want to say is torsion was considered all these weeks. Okay, I mean they introduced it several weeks back, and they have been working with torsion for some time now, right? Because you have been considering Jordan canonical form, rational canonical form, and all that. Anyways, I'll just repeat it once more for you. What is, suppose M is an A module. Okay, what is the torsion part of M? It is precisely the set of elements M in M, which are annihilated by some ring, non-zero ring element, such that A dot M is equal to 0 for some A non-zero. Okay, this is what torsion is. And if the base ring is an integral domain, then torsion of M is a submodule of M. That's it. All elements which are annihilated by some element, by, I mean all those elements which are annihilated by some non-zero element of the ring. Okay, that is what torsion is. So now we want to know why torsion part of ma is equal to ma. In other words, what we want to know is that if you take any element of the module ma, of the ft module ma, then it is actually annihilated by some polynomial, right? Non-zero polynomial. In other words, so anyways, let me not write it all this. Write all this. So what kind? Yeah, but let me ask you. Suppose you take. Yeah, I'll write it, but let me just ask you. Torsion part of ma is equal to ma. This is what we want to show, right? If you take any element of ma, it will be annihilated by some scalar, non-zero scalar from f. So can you give me an example of a scalar which, I mean we are claiming something more here, right? Not just the fact that if you take an element from ma, it will be annihilated by some non-zero element of ft. What I am saying is there is there is some non-zero element of ft which actually annihilates every element of ma. It's not that, no. What do you mean by the basis element here? So what I want is, so so for B it is true that torsion part of ma is equal to ma, but we are claiming something more here. So the claim is there exists a polynomial pt in ft such that pt dot ma is actually equal to 0. What I mean by this is that every element of ma is annihilated by this single polynomial pt. It's not that if you take an element you have some polynomial which annihilates it. If you take a different element you might have a different polynomial which annihilates it. Okay, this is not what I'm saying. So there exists some non-zero polynomial pt which actually annihilates every element of it. This is what we are saying. The first statement is yeah. So torsion of ma is equal to yes. Sorry. Yes. 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 So saying that torsion of ma is equal to ma is not the same as this one. Okay, torsion of ma equal to ma means that you take any element of ma, there is some non-zero polynomial which annihilates it. So you could take a different element of ma, you might get a different non-zero polynomial annihilating it. But what we are saying here is that there is a single polynomial pt non-zero in ft such that pt annihilates every element of ma. We can find a single polynomial which does the job. We don't need different polynomials for different elements. Okay, this is what we are saying here. So what is that polynomial? It's very easy. It is the characteristic polynomial, or let's say we can even take the minimal polynomial, right? Any polynomial annihilating a will do the job. So it is the characteristic polynomial of the matrix A. Okay, so for example I should write, it's not unique. For example, characteristic polynomial of A, for example p of t is equal to characteristic polynomial of E, right? Why? This is because pt dot ma, what is this? This is just, by definition this is p of a acting on ma, but we know that the characteristic polynomial annihilates the matrix, right? This is what the Cayley-Hamilton theorem says. So this is zero, the zero operator acting on ma, so this is just 0. Okay, as simple as that. So this is where we are using the Cayley-Hamilton theorem. So this question was not a part of your previous year assignment. I just sort of put it in. Anyways, we are left with 2 problems and they will be solved within 5 minutes. We just need to, this is all about the Jordan canonical form of the matrix. I hope you are okay with Jordan canonical form right now. This was taught this particular week, right? Still, if you have questions, you can ask me. So anyways, so let ma be ct modulo t minus 2 whole cube direct sum ct modulo t minus 2 direct sum ct modulo t minus 3. We are asked to find the Jordan canonical form of it. Now the module ma, we have already expressed it from using the structure theorem for finitely generated modules over a PID. The PID here is ct just, okay. And not only so, we have expressed in the primary decomposition form, right? That is, we have written it explicitly in terms of all the primes that there are. So yeah, so ma is isomorphic to ct. Let me just write the powers in order. Direct sum ct t minus 2 whole cube direct sum ct t minus 3 ideal given by t minus 3. So yeah. So this is what ma is, and therefore the Jordan canonical form is. So just write the Jordan canonical form, and How do we do so? We just look at the various summands here. Ct modulo t minus 2, right? This will, you know what its Jordan form looks like, or the corresponding Jordan block looks like. Since the power of t minus 2 is 1, so the Jordan block will have order 1, right? And this corresponds to the eigenvalue 2, right? So this is one Jordan block. And then you have Ct modulo t minus 2 whole cube, right? So the power is 3 here, which means that the corresponding Jordan block will be a 3 cross 3 matrix. It will correspond to the eigenvalue 2, and it will look like 2, 0, 0. Then you have 2 here, you have 2 here, and you have 1 here, right? This is what the Jordan block looks like for t minus 2 whole cube, right? Isn't it? Right? Yeah. And finally, what does the Jordan block for t minus 3 look like? It simply is 3. It's a 1 cross 1 block, and it is simply 3. Corresponding to the eigenvalue 3, it looks like this. So just recall what the Jordan block for t minus lambda power k looks like. I mean Ct modulo this. The corresponding Jordan block is basically lambda 0, 0, 0. Let's say it will be a k cross k matrix. You have lambda in the leading diagonal, so you have zeros here and all that, and you have ones in the off diagonal position, and rest of it as 0, right? This is what we have done, right? Precisely this is what we have done. So in this case we have 3 Jordan blocks. There is a 1 cross 1 Jordan block corresponding to 2, there is a 3 cross 3 Jordan block corresponding to 2, and there is a 1 cross 1 Jordan block corresponding to 3, and the rest of it are just zeros. So 0, 0, 0, 0, 0, 0, 0, 0. Right. So this is what your matrix looks like. Okay. So this is the Jordan canonical form of it. Is it? I mean, you understood, right? So this is precisely the decomposition. So it's a block diagonal matrix as the Jordan block looks like. I mean Jordan canonical form is, and similarly the rational canonical form, as you know, is also a block diagonal matrix. Anyways, let's move on to our final problem. So we are given a matrix A and we are said that its Jordan canonical form is this. Okay. Then we need to find out the module MA. Okay. Again, very easy. Just decompose the given matrix into its various Jordan blocks. So, so you have 2 0 0 0, 1 2 0 0 0, 0 0 2 0 0, and you also have, oh okay, so the first Jordan block is this, right? Because after that you don't have a 1, right? In the third row, second column, you have 0, you don't have a 1, right? That means the Jordan block ends above, right? The first Jordan block, it's 2 0 1 2, and then again you go along the diagonal, you see that 2 0 0 1 2 0 0 0 5. So that means again this is another Jordan block, right? 2 0 1 2, again this is a Jordan block, right? Because after that you have a 0 instead of a 1, right? I mean in the last row, fourth column, you have a 0 instead of 1. That means the Jordan block ends above it, which means that again you have a 2 cross 2 Jordan block, 2 0 1 2, right? And finally you have a 1 cross 1 Jordan block which corresponds to the eigenvalue 5, right? That means MA is isomorphic to what? So we are assuming, since we are taking algebraically closed fields, we are taking C for example. Okay, we are working over C. So MA is isomorphic to CT modulo. So what is this? What is the first Jordan block? It corresponds to the eigenvalue 2, right? 2 0 1 2. It corresponds to the eigenvalue 2, and its order is 2. That means it's CT modulo the ideal giant by t minus 2 whole square, right? Direct sum, again you have a Jordan block 2 cross 2 size, 2 corresponding to the eigenvalue 2. So this direct sum CT modulo ideal giant by t minus 2 square, right? And finally you have a Jordan block corresponding to the eigenvalue 5, a 1 cross 1 Jordan block. That means the power of t minus 5 should be 1. So just the ideal giant by t minus 5, and this is your MA. Okay, it's as simple as that. Yeah, okay. So that brings us to the end of this. Yeah, yes, the direct sum of all this, right? This is the structure theorem, right? You can write ma as a direct sum of this ct modulo something, right? Copies of ct modulo something. I mean, not copies of ct modulo some ideal gent by some prime power, direct sum ct modulo ideal gent by some prime power, and so on. And there will be finitely many direct summands in this because ma is always finitely generated, right? So anyways, do you have any more questions? Ah, yeah, sure, definitely. You know my email ID, right? Yeah, surely, definitely. And this sort of brings us to the end of this session. This is our final week, week 12, and yeah. So if you don't have any questions, I'll just stop the recording right now.